For a really long time, individuals have imagined what life may resemble in different universes. Considering the James Webb Space Telescope, the most stunning telescope in existence, that question can finally be examined. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, specialists have seen a couple of unusual anomalies from one of the planets in the system, Proxima B. These anomalies, called artificial lights, have confounded the best minds in the area of science. Anyway, are they? Do these lights suggest the presence of intelligent life? Join us as we look at the James Webb Space Telescope's disrupting discovery of city lights that could change everything. The main life that we are currently aware of is on Earth. Since the start of human civilization, people have contemplated whether there is life elsewhere in the universe. To answer such an interstellar question, American cosmologists Jill Tarter and Thomas Pearson launched the Search for Extraterrestrial Intelligence (SETI) project in 1984. The primary goal was to gather spaceborne radio transmissions. Radio waves can travel farther and are consequently bound to be detected by the 42 radio telescopes that make up the unprecedented Allen Telescope Array in the California Lower District Mountains. However, for more than 30 years, no prominent extraterrestrial transmissions had been found. Following that, the James Webb Space Telescope's successful launch helped the work to examine a range of invisible planets orbiting distant stars. As the largest telescope on Earth, floating around 1 million miles from Earth and equipped with highly sensitive detectors, it has the potential to make monumental discoveries. Years ago, there were no known planets outside our solar system. However, since then, more than 4,000 exoplanets have been discovered orbiting various stars, as illustrated by NASA. The universe could contain trillions of exoplanets. The earliest signs of something occurring far beyond our solar system may be found in extraterrestrial vegetation. The Galileo spacecraft, en route to Jupiter, turned its instruments back toward Earth and saw an obvious indicator of the presence of plants, recognizing the vegetation red edge, a biosignature, a mix of red and infrared light reflected by plants. For instance, a planet like Earth, covered in wild vegetation, should have an obvious area of strong markers, easily detectable. The JWST will measure the VRE of distant, Earth-like planets in the habitable zone around stars, which could give critical signs of something happening in the exoplanet's atmosphere. When light crosses a planet's star boundary, the JWST might be able to detect it as it enters the planet's atmosphere. The missing frequencies would then be visible through spectroscopy as particles and ions in the atmosphere absorb specific frequencies, creating a distinctive fingerprint that the JWST can recognize. This technique could be used to determine the composition of the atmosphere and whether life is possible. Life could exist on Earth-sized planets with atmospheres like our own, characterized by a mixture of oxygen, nitrogen, and carbon dioxide. By looking for components that aren't commonly present, one could even identify intelligent life. For example, chlorofluorocarbons, CFCs, made for use in refrigeration and cleaning products, would likely be detectable by extraterrestrials studying Earth's atmosphere from a distance. If the JWST detects CFCs in planetary environments, it could suggest the presence of life. However, life on exoplanets likely won't resemble life on Earth in any way. Sometimes, even regular living organisms, like extremophiles, species that can survive in conditions where other living things would perish, may appear alien. This group of life forms, primarily microorganisms, can survive extreme conditions, such as temperatures up to 250 degrees Fahrenheit or strong acids with pH levels under 3. Since planets are more likely to support life if they don't have extreme temperatures or acidic conditions, it may be wise to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is a yellow G-type star. These stars are rarer and typically have shorter lifespans. However, in our galaxy, the chances of finding planets orbiting red dwarf stars, more common, cooler, and dimmer than our Sun, are higher. This long lifespan allows for the development of life and evolution to produce complex organisms. Around 40 light-years from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It orbits a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets, located in the so-called habitable zone, could have liquid water on their surfaces. Despite its smaller and colder mass compared to our Sun, the TRAPPIST-1 star emits light similar to Earth's, which is enough for the planets in its vicinity. The most likely chance to observe city lights outside our nearby solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Proxima is generally fainter than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 Earth masses in this habitable zone, a Goldilocks-like zone where the light intensity is ideal for liquid water. Proxima B orbits Proxima Centauri, but the fact that Proxima B is tidally locked makes it a potentially airless, dead planet. Since it orbits its red dwarf star only 4.6 million miles away, this close orbit exposes it to strong solar winds that could strip away its atmosphere. However, Proxima B receives enough light for temperatures and liquid water similar to those on Earth, due to its proximity to the star. Proxima B is believed to be tidally locked, meaning it always shows the same side to the star, much like the Moon does relative to Earth. Proxima Centauri is about 18% the mass of the Sun and emits much less light than one might expect for a planet so close to the star, around 5% of the Sun's power. This would seem like a barren wasteland, but liquid water could exist on Proxima B if the planet has an atmosphere to retain heat. Since the total energy reaching from the Sun is only 65% of what Earth receives, the planet is not especially promising for life. It is likely tidally locked, meaning it always faces the same side toward the star, creating a permanently hot side and a cold, dark side with extreme temperature variations. The planet also receives multiple times the high-energy radiation that Earth does, including X-rays and ultraviolet light. Due to its closeness to Proxima Centauri, Proxima B is also bombarded with high-energy particles during stellar flares. Unless it has a protective magnetic field like Earth's, conditions may not be suitable for life. Despite these harsh conditions, Proxima B may still be a more habitable world. Sadly, models suggest that the atmospheres of tidally locked planets may be prone to rapid erosion due to the freezing out of volatile gases on the night side. Earth's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, their atmospheres are less likely to escape. Since we don't know anything about Proxima B's volcanic activity or magnetic field strength, we can't speculate on whether the planet has an atmosphere. However, since an atmosphere suggests the possibility of life, we are eager to learn if Proxima B has one. It could have solar panels on the day side to generate power for lighting and heating the night side, which would otherwise be too cold and dark for habitation. The discovery of Proxima B has sparked a race to determine whether it crosses its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, which would help them estimate its density and confirm its rocky composition, providing information about the materials used to form those rocks. During a transit, starlight could reveal the planet's nature by passing through its atmosphere. However, the chance that the orbit will be perfectly aligned so scientists can observe a transit is only 1.5%. The star's tendency to emit further complicates matters. Cosmologist David Kipping of Columbia University says the star is unstable, as stellar radiation causes a rocky planet to absorb sunlight and re-emit it as infrared light. However, rocky planets produce a particular kind of infrared radiation from stars like Proxima Centauri. Additionally, the James Webb Space Telescope was specifically designed to detect infrared light. Proxima B's infrared signature is crucial for identifying the planet's atmosphere. Also, the JWST's infrared capabilities, which surpass those of the Hubble Space Telescope, could allow it to detect city lights on the night side of the planet, even if they are as faint as those currently used on Earth. The JWST could detect artificial lighting as long as it falls within a frequency band much smaller than the star's light. Proxima B's day side may be heavily covered with solar panels reflecting starlight as Proxima B orbits its star. Constantly, the varying sides have extreme temperature differences between them. The temperature contrast between day and night depends on whether the planet is made entirely of bare rock or, alternatively, if air and water circulate heat. If there is no atmosphere, Proxima B's day side and night side temperatures will vary more, as the day side will radiate all the energy it receives from Proxima Centauri as infrared light. The night side would resemble a frozen wasteland. If the temperature difference between day and night is less pronounced, we can estimate that future space exploration and the search for life beyond Earth hold tremendous potential. The James Webb Space Telescope, JWST, might be the key to discovering extraterrestrial life in the universe as the JWST searches for exoplanets. It will ultimately provide us with a clearer understanding of the potential for life beyond Earth. The telescope's capabilities, particularly in detecting faint signals from distant worlds, offer unprecedented opportunities to study planetary atmospheres in great detail. By analyzing the composition of these atmospheres, scientists could identify chemical markers that suggest the presence of life, such as oxygen, methane, and other gases that are typically associated with biological processes. Moreover, the detection of artificial lighting, city lights on a distant planet, would be a groundbreaking revelation. If the JWST is able to spot such lights on a planet like Proxima B, it could indicate the presence of an advanced civilization. This discovery would radically transform our understanding of the universe and our place within it. The idea that intelligent life exists elsewhere in the galaxy has long been a subject of speculation, but the possibility that we might one day have concrete evidence is now within reach. As the search continues, the JWST's findings will undoubtedly reshape the field of astronomy and astrobiology. The telescope's ability to peer into the atmospheres of exoplanets, study their potential habitability, and detect signs of life will drive future missions and scientific endeavors. The quest for extraterrestrial life is far from over, but with the power of the James Webb Space Telescope, we are closer than ever to answering one of humanity's most profound questions. Are we alone in the universe? In the coming years, as more data is collected and analyzed, we may begin to piece together a clearer picture of the conditions that allow life to flourish. The discovery of life beyond Earth would not only confirm that we are not the only intelligent beings in the cosmos, but it could also provide valuable insights into the origins of life itself and the potential for human expansion into the stars. As the James Webb Space Telescope, JWST, continues its observations, the possibilities for discovery grow even more exciting. Beyond just detecting signs of life, the telescope could reveal new details about the diversity of exoplanets, including those that might have conditions similar to Earth. Scientists are eager to explore whether these distant planets possess the necessary ingredients for life, such as liquid water, an atmosphere, and stable conditions. In fact, the JWST's ability to study the chemical makeup of distant planets could help scientists understand more about how life might arise and survive in environments very different from Earth. One of the most compelling aspects of the JWST's mission is its potential to identify biosignatures in the atmospheres of exoplanets. By looking for gases that are produced by biological processes, such as oxygen, methane, and nitrous oxide, scientists could uncover evidence that life exists or has existed on faraway worlds. These findings would provide a major breakthrough in the search for extraterrestrial life and challenge our assumptions about the uniqueness of life on Earth. In addition to its focus on detecting life, the JWST will also help astronomers understand the broader cosmic context in which life might emerge. By studying the formation and evolution of stars and planetary systems, the telescope will give us new insights into the conditions that are most conducive to life. It will also help identify new star systems and planetary environments that may be worth further investigation, potentially leading to future missions to explore them up close. As we look to the future, the JWST's discoveries could pave the way for a new era of space exploration. If the telescope identifies planets that seem to have the necessary conditions for life, it could lead to the development of next-generation space missions that would aim to explore those worlds directly. This could include sending probes to study exoplanets up close, searching for signs of habitability, and potentially even sending humans to explore these distant worlds in the far future. The JWST's role in answering fundamental questions about the existence of life beyond Earth is just the beginning. With its extraordinary capabilities and groundbreaking research, the telescope will continue to shape the way we think about the universe and our place in it. Whether we find evidence of life or not, the search itself will inspire future generations of